Okay, thank you very much. Thank you for the invitation. It's a pleasure to be here at B-Sides Munich and to talk about embedded security, which is something different from what we hear this morning. But it's interesting, I can promise you. My name is Sebastien. I am what is called a security researcher. And I'm especially interested, obviously, in embedded devices and hardware security. My favorite topics actually are side channel attack and fault attacks. Now, to set the expectation today, there won't be any side channel attacks and fault attacks in this talk, but I promise you it will be interesting even without them. So please stay. And yeah, this is a joint work I did with Davin. It was an excellent teamwork. We learned a lot from each other. And you see here our Twitter or X or whatever it is called now handles if you want to contact us. Agenda. First, I will present you the target of evaluation, so the device, which we had a look at. Then we will go into the main story, which is getting root privileges in this particular device. Then we will have a look at the firmware upgrade process, and some interesting vulnerabilities there. And at the end, some stuff about cloud connectivity, because, yeah, everything ends up in the cloud today. And we will conclude. So the target of evaluation is a router. I wrote it here, from the company called Cradlepoint, which is a US-based company. This company is maybe not that well known in Europe. It is now part of the Ericsson group, just to know. And it's what they call a semi-ruggedized router. Yeah, you see it. It's not like the router you have at home. It's a little bit more ruggedized. Used for public safety. That's a station from the website. Public safety support for mission-critical IoT. I guess it is like fire brigades and police. It's a router, so it has a lot of connectivity. So we have Wi-Fi, for sure. We have an LTE, 4G modem, LAN and WAN connections, and, of course, cloud. So this device will connect to an own cloud, so the cloud from Cradlepoint, which is called NetCloud for device and fleet management. It has also an internal web server for configuration. And as you see here on the right side, this is from ZoomEye. You see how many devices are now accessible in the internet. So I mean, they are accessible as a server, right? Not as a client. So to sum up, this guy here has a very wide attack surface, so a very large attack surface. We can have a look at many different things, so we had to focus a little bit. We obviously had a look at what was already done on this device. Not much was public, so there is this website here. Someone disclosed some vulnerabilities, and you see here a lot of hard-coded credentials, which is somehow typical for embedded devices. So you may have some maintenance account or whatever with a hard-coded password. Not that good. But on the positive side of things, they fixed everything. So we had the chance to check, and everything which has been disclosed was already fixed. And again, lots of hard-coded credentials. This is something we see a lot in embedded devices. And now let's open the box, right? So you don't see it, but yeah. And sorry for the mess. I added some specific features here. So what do we see? First, we see on the left side here the main CPU, which is a Qualcomm CPU. No surprise here. We have a router, so Qualcomm. This CPU is connected to SDRAM. Now, DDR3, it's not that new. You see these metal cases, so you don't see the SDRAM chips, but there are metal cases. The reason is EMI, because we have a router, so we have a lot of analog signals here, RF signals, dealing with a lot of RF signals. So, and this guy here is producing a lot of perturbation. So everything which is switching a lot, so like DDR, SDRAM. So therefore, they put it under this case and hope that it will be quiet. On the bottom, the thermal pad over a modem, so a 4G modem. Fascinating stuff, but not part of this evaluation today. But if you have a look what people are doing now with 4G or whatever modem basement stuff, is just fascinating. So the microprocessor does not have any embedded flash, so it needs some non-volatile memory. And we have a typical combination here of NAND flash and NOR flash. So NOR flash is more reliable, so it is used for the boot process, but it is also more expensive. And NAND flash is used for the root file system, the application, user data, and so on. And some stuff here related more to the power supply. So what's the beginning of this adventure? So now we know a little bit more about the architecture. Let's have a look at the boot process, which is always something, as a security researcher, you will always have a look at it, and there are some interesting stuff here. So we were looking for a serial interface, UART. Normally, this kind of serial interface at boot time gives you some information about the boot process. So what kind of bootloader is used, how is the boot process. And we found here on the right side the UART pins, but it was not talkative at all. So it just gave some very limited information about a Qualcomm bootloader, and then it stops completely. So now the challenge was how to make it a little bit more talkative. So, and for that, we had a look at the NOR flash. As I said, the NOR flash, so the non-volatile memory, contains the boot information, so the boot loader itself and some variables. And to dump the NOR flash, I use my favorite tool, the bus parrot, which is, and with FlashROM together, and with that, it's very simple. You can dump any small SPI NOR flash. So SPI is the communication bus used between the microprocessor and the NOR flash. And then we found out that U-boot is used. So U-boot is a typical bootloader for embedded devices which are using embedded Linux. And with U-boot, U-boot is using what are called environmental variables. And these variables are mainly stored in plain text, so in strings, in ASCII strings, in the binary or outside in a specific file. In that case, it was embedded in the binary. And you can see here a few of them. And especially, there is one environmental variable, which is called silent. And you guess what? It was set to yes. And you guess what? We set it to no. So we just remove this and set it to no. And then, we got a U-boot console, which is a very nice achievement, right? Everybody wants a U-boot console. And with the U-boot console, you can then do a lot of more stuff, like having a look in the flash and downloading some file into SDRAM via TFTP and a lot of fascinating stuff. So an interesting point is that we were able to change the variable, and the device boots without noticing it. So, because secure boot is not in place. So secure boot is here, normally, in embedded device, especially important, to prevent this kind of stuff. So normally you will sign every piece of software, which is going to run in your device. And then at boot time, the processor system will check the signature before it executes this particular piece of software. And this is not done here, right? And to do that, you need a public-private key system. And for signature verification, obviously, you just need the public key, which you put normally in the microprocessor itself, so in so-called fuses. So it's a kind of mini non-volatile memory which can be used for that. And here, again, no secure boot, so we can change the environmental variables, and we get a U-boot console. Okay, now we have the content of the NOR flash, and as I said, there is a NAND flash, which is much bigger, also much cheaper. And this NAND flash contains the root file system, the kernel, the application, and a lot of user data. So now NAND flashes are a little bit more complicated to dump, right? Because they have all this bad box management, ECC and stuff. They are not that reliable, so you need a software layer on top of that. You cannot access them just raw. And unfortunately, Bus Parrot and FlashROM do not support that. So now the idea here was to record the SPI activity. So as I said, the SPI is the bus between the microprocessor and the flash. To record the activity of the SPI bus during boot, and then extract this information to have the root file system and the kernel. And we did that with this excellent logic analyzer here, the Salih, I don't know how to pronounce it in English actually. And you see there are blocks of data, and this guy can also decode all the SPI's information. And then with a few scripts, we were able to remove the handshake information between the blocks, right? You have some handshake, so you need to concatenate everything. And then we add everything, the root file system, the kernel, and that's it. No surprise here, the root file system, as you can see here, is in SquashFS format. SquashFS is mainly used also in embedded devices. But a very big surprise for me was that the middleware or application was in Python. Python in embedded was, for me, was new. Another point is we were able to extract this data because they were not encrypted, obviously. What you can do here, if you want to prevent this kind of attack, you can encrypt your data at rest in Flash. And then in the boot process, the microprocessor will decrypt the data, puts them in the SDRAM in plain, and afterwards it runs from the SDRAM. However, and then it comes to side channel attack, then you can do side channel attack because the key is in the microprocessor. You cannot just extract it, so you can measure some physical emanations, and with a kind of magic, then you get the key. Yeah, it's very, very short. But anyhow, you can do also what we call a cold boot attack, because as I said, this information will be stored in the SDRAM in plain. So if you are able to put firmware inside the microprocessor, so you do a reset without switching the device off, then the data will be in the SDRAM. So there will be a remnant in the SDRAM, and you can extract the data of the SDRAM. This is also another possibility. Okay, now let's have a look at the application of the middleware. So as I said, Python is used. Quite fascinating, but not the Python code, obviously, is stored in the device, but the bytecode, so a kind of compiled code. This can be very easily decompiled. There are tools out there like this decompile 3, and obviously can be recompiled. So you can decompile it, patch it, recompile it. And here is an interesting script which runs at boot time, which they made to reactivate the silent mode in case some people like me try to deactivate it, so it will be reactivated. And you guess what? We patched also this script so that we have no problem with this silent mode. But you see here, it's very nice, right? It's just decompiled from the device. So you see Python script. Nothing like binary and so on. So it's from an attacker perspective, it's very nice. Okay, now our goal is to get root privileges. In this device, there is a shell implemented, which is called the CP shell, I guess for Cradlepoint. This shell is accessible via SSH or the web interface, but it is very limited. It is not a full Linux shell. And now we found out in this CP shell script, which is also a Python script, that there is a protected command called sh, which reactivates or activates a full Linux shell. And the goal here now is to patch this particular Python to reactivate this sh command. And you see here, normally, if this super user variable is set to true, then it will be activated. Otherwise, it won't be activated. And the result is just an OS command, right? Bin sh, and that's all. So, unfortunately, in that case, it was not possible to decompile this big Python script. It was quite big, error-free. It happens a lot. There is no, decompile 3 is very good, but a lot of times we had trouble with decompiling. So in that case, we had to go to the next level, to the assembly level. And there is, interestingly, also an assembly level in Python. You can disassemble the code with this tool. And then you see these kind of things. It is still very readable, right? You see all the variables in plain text and the line of code. So to find out the right place was not that difficult. And here you see a branch, jump if false, and we patched it with jump if true, so that the variable, the command sh was reactivated. There is a pitfall here because the opcodes of Python are changing with each Python version. So be careful. If you do that, try with this module to get the right opcode, so the right binary for each opcode, the right value. And then you take your favorite hex editor and you patched the right position, so where the opcode is for the jump if false, and you patched it to jump if true. And yeah, this was a workaround in case a Python bytecode is not decompiled error-free. And now we are almost here. We still have to reflash all that root file system inside the device. And as I said, flashing and non-flash is a little bit complicated. But we have a U-boot console, right? And with a U-boot console, you can download via TFTP a live image inside your SD-RAM and run it from there. And then the idea here was to take a live image from this open source project, OpenWRT. Probably you know it. It's an open source project for routers, so they provide you with images for your particular router. And in that case, there was no image for this router, but there was an image for this microprocessor, so for the Qualcomm one. And we tried this out. We had to modify a few things, and then it worked, right? We got a Linux shell via this live image. It has nothing to do with the Cradlepoint firmware, but we have a live image, a live Linux image working on the device. And then we have the layers which we need to flash the non-flash, which I call this UB layer. So we need this UB layer to flash the non-flash because as I said, we have this bad block management, for example. And so we need this layer. And with these 3 commands here, it was possible to reflash here the kernel, but you can do the same with a root file system. And with that, we were able to reflash or patch version of the firmware. And we reboot it, and the sh command was activated. And so we had a Linux shell. And with that, that's the end of the first story. To sum up, we first dumped all the content of the NOR flash of the non-flash. We had a U-boot console. Then we were able to patch the application, which is in Python. Python bytecode, okay, you have to maybe go to assembly, but it's not like assembly from a binary, it's much easier. And then reflash on the device, and then you get a root shell. End of the first story. Now let's have a look at some other interesting stuff. Firmware update, which is also something extremely critical and extremely interesting. Of course, you need firmware update to patch your device. But on the other hand, if you are not careful with the security of this firmware update process, you may get into very, very big trouble. Because if an attacker is able to put a firmware like we did here locally, then it's gone, right? It's permanent in the device. So this is very important to secure the firmware update process. And yeah, there are a solution for that. And here we downloaded some images from the web server. So the firmware update process is now based on the cloud, which is state of the art, but they still have some older firmware update images in the web server and for OSINT, so we decided to download it and to have a look. The firmware update images were encrypted, which is good, but obviously there is a global key there because of logistical reason, right? You cannot encrypt if you provide a binary or a data image in your website, you cannot provide it encrypted for each device. Or let's say it's much more complicated. So now we have the content of the root file system where the firmware will be decrypted. So we have to have a look where the key is. Now here, in that case, it was a little bit obfuscated, but still it is in the root file system, right? This is not a problem to get the key. Now, as I said at the beginning with the secure boot, there is also a possibility here to do it a little bit better if the hardware has the capability. You can also put this key into fuses so that an attacker cannot just get the key from the root file system. Okay. Now we decrypted the image and saw that there are 3 parts: a header with a version string, the body, and the signature. Now, interestingly enough, the signature is only computed on the body, not on the header, so the header is not protected. So, first problem. Second problem, these lines of code. If the version is less than this number, then signature verification will be skipped. Now we see all the problems together. You just have to put a string here, which match to a version number which is less than that. And then you can do whatever you want. You put whatever signature you want, the device will accept it, because it's, unfortunately, because of legacy reasons, probably, it is there. Which means Secure Boot is completely broken. It happens, unfortunately, a lot. But they patched it. Okay. And now we go to the last stories, because every IoT device nowadays is connected to some kind of cloud. So we decided to have a look at the cloud communication. So this device connects to its own cloud, the net cloud, via TLS. Super. But yeah, but now we have the root file system, and there is no Secure Boot, so that we can add our own root certificate to the trusted store, and the device will just trust it. And this is also a problem if you do not have Secure Boot, or if you do not have integrity protection of your trusted store. Right? The word trust is not here for nothing. And if you can patch it and add an own root certificate, then you can use this very nice tool here, the man-in-the-middle proxy, to decrypt the communication. So basically, you put in the trusted store the root CA of the man-in-the-middle proxy, and then it will build a communication to the man-in-the-middle proxy, because it will trust the root CA of the man-in-the-middle proxy, and then man-in-the-middle proxy talks to the cloud server, and then you can decrypt the communication, man-in-the-middle, right? And as I said, this is very important to take care about integrity of your trusted store, especially in embedded devices. And then we found this one, and this is the best one, right? We had a look at the traffic, and we found out these lines here with this base 64 encoded string. And it came out that this is a serialized Python. And in Python, I didn't know that, there is also a serialization module, which is called Pickle. And if you have a look at the website, the documentation website of this module, there is a big red warning, right? It is not secure. And the reason is, and it's quite fascinating for me, coming from more for the hardware side, you can just, with these few lines of codes, execute OS command on the remote side. And then with this command, you will probably understand what it is. It's a reverse shell, right? So you get a reverse shell on your side. So takeaway here is be careful not using Python this serialization in some data that you cannot trust. And here, since we add the possibility to decrypt and to change the traffic, we were able to change this particular string. And we did that in the other side, so not on the server, obviously. But the device itself has the same capabilities. So we injected these lines of codes, and we got a reverse shell from the device now. And if you want to have a look, if you want to have details about this Python pickle and how to exploit it, there's this very good blog post here, which gave all the information. Yeah, so obviously serialization is not only in Java, it's also in Python. It's very, very dangerous. And the last one was related to registration. So we had the root file system, and we found out a function called insecure activation. Now, with that name, we had to have a look at it, right? Maybe it's a honeypot, but no, it was a real. So they used that to, activate devices just based on its MAC address. And now this function took the MAC address as an input, did some kind of magic, and you got a string out of it. And with this string, you could get some authentication token in the cloud. Because, as I said, or I didn't say that, but the TLS connection there is only server-side authentication. And this is a very big problem in embedded. If you have only server-side authentication, like you have if you go in the internet, then how are you sure that the device is the real device? And that's a very a very big problem in embedded. If you do not have a proper client, certificate-based client authentication, which we call mutual TLS or MTLS, then you always will end up into this kind of problems, so MAC address or serial number or whatever, which is definitely not the best thing to authenticate a device. And yeah, long story short, with this token, we were able to disconnect any device from the cloud, so from their own cloud, just knowing their MAC address. And without having anything, right? No device, nothing, just having a look in eBay or whatever, you find some MAC addresses, and then you put it in the insecure activation, get the strings, get an authentication token. With this authentication token, we were able to just say, I am this one. And then the other one, the real one, was disconnected. And that's it. So, logical problem, I guess, in this. Okay, as I said, without client certificate, you will get device authentication will be tricky. And now I come to the conclusion on time. We communicated our results to the company, and they had a very prompt and professional reaction. Almost all the vulnerabilities have been patched. I said almost because, for example, secure boot cannot be just patched by software. You need the hardware capabilities. As far as I understood, the newer devices, they have secure boot. And now there is a kind of advertisement block at the end for embedded security because it's fun, right? And as you saw now in this talk, it's okay, not everything, but you will touch many, many different topics. From hardware, so like dumping flashes, sniffing some interfaces, even soldering wires if you can. I cannot do that well. Then operating system, boot process is also very interesting. Operating system, embedded Linux here. Networking, TLS or MTLS, if you're lucky. And at the other side, of course, all the cloud and the web stuff. So a lot of different topics there. You can learn a lot. And the second thing is the IoT devices are very, very diverse, right? You can have a very small IoT device based on STM32 or something like that. Bare metal, embedded flash, embedded RAM, nothing. And on the other side, you could have like a full-fledged PC, right, with a high-end NVIDIA GPU and gigabyte of RAM and flash. So also here, quite fascinating. End of the advertisement and end of this talk. If you want to have more details about this device, all the details, we documented all the details in the GitHub here. And there are also more interesting stories, so please have a look. I hope you enjoyed. Thank you for your attention. I think we still have a little bit of time for questions before lunch. Thank you very much.
So thank you very much, Sebastien, for the talk. Super interesting. And I agree, embedded security is definitely fun. There's a lot of stuff to find. We do not really have time for questions because it's 1 p.m. and I think you all want to go for lunch. But just find Sebastien during the lunch break so you have something to talk about.
For sure.
And we will continue the session at 2 p.m. So all I can say, thank you again, give it up for Sebastien and enjoy lunch.
Thank you very much.